Hi, this is a presentation on a research in relation to suppressing background noise in a conference, BBM Enterprise conference, using machine learning. And in this particular research, we will demonstrate how a recurrent neural network can be used to eliminate background noise. So the research problem first. So as we've all experienced in video conference calls with many participants, they typically expose unwanted background noise if they forget to mute their microphone, and especially if they're not speaking. And it creates a very noisy environment. And with the recent advancements in background noise separation from speech, typically what we've seen with papers published and also product integration, they're leveraging a cloud-centric processing of the audio streams. In other words, the suppression occurs in the cloud. Now, in this research, our goal is to develop a noise and speech separation solution that can be applied on the edge, on the BBM Enterprise app, or even on a browser running the BBM Enterprise conference. So we want to do the processing of the speech separation and noise suppression on the edge. With our focus on end-to-end encryption and on privacy, doing this on the edge may address our customer needs in regulated markets. Most of our customers in the law enforcement, they're out in the streets, and when they're using this, they might experience a lot of background noise, at least to people who they're talking to. And in those privacy-focused customers, a edge-based solution may be more realistic or preferable. So the challenge. Audio distortion is very susceptible to us humans. Thus, a real-time processing speed needs to be quite fast. And in video, for example, if you have a little bit of a jitter or a buffering, it kind of smooths itself out. In our eye, natural cutoff frequency being 3 kilohertz, we're not able to always discriminate between those. But audio, we're very sensitive to changes or in distortion. So the entire process needs to be extremely fast and in real time especially. So let's take an example. What does that mean? Let's say each frame is 512 samples, and at wideband, which is what we operate at, 48 kilohertz, that's about 10 milliseconds each frame size. If you were to downsample it to 16 kilohertz and reduce the band, it would be about 32 milliseconds. Most solutions out there today process 16 kilohertz audio for the purpose of background noise suppression, as it lends more processing time. And while the results are quite good, however, the fidelity of the output, because of the narrow band, is lost. So in this research, we intend to work with 48 kilohertz band and maintain a high fidelity audio experience. Which may mean that we may have to adjust the depth of the neural network, since our target median goal is to process the audio frames, with a mean distribution of 5 milliseconds, thus giving us enough capacity to fit within the 10 millisecond boundary, considering the edge device may be busy, the CPU might be doing other things, such that for conference purposes, it should not be doing any additional processing, or if it slows down, it might cause audio challenges. So the way we set it up is we take some of the classical signal processing approach as published in research elsewhere and use it to extract the input features to target an output. So what we do is the setup as shown here, as per our research paper outlined. We apply the same modeling technique whereby we take the input frame to a Hamming overlap and extract the FFT, and then a short time Fourier transform actually to perform the magnitude extraction, and SDLP, which is a short-term log power spectrum estimation to understand what the distribution of the energy, and basically that feeds into some feature extraction mechanism. And what we get out of it is the real magnitude gains for each bands. So we take the entire spectrum of 48 hertz, we chop it up into 22 bands, and then apply this process to understand how these features are present in each of those bands. The pitch filter, as you see here in the middle, which basically performs a summation operation after the band gain interpolation, is there to cancel out any interharmonics noise estimation. So for instance, when you're speaking, and you pause and you speak again, if there is noise in between, or if it's mixed with other harmonics of the vocal range, those need to be extracted. So 22 bands is what is used as per the Bark scale, which is typically the range of a human voice scale. Features such as pitch, energy, septal delta for each of these bands comprising of 42 feature set is extracted through this pre-processing stage of the input signal. Then comes the AI part. We use recurrent neural network. Basically, RNN introduces an internal state at each node. Thus, we can encode long-term temporal pattern and cross-frequency information within the time series signal, which is the voice audio signal. There are 3 RNN layers, as you can see, identified. They're responsible for speech and gain outputs. And if you look at the top layer, the input comes in and it basically produces 2 outputs. One is a VAD output, which is a speech detection voice activity output. And the other one is the gain output, which is estimated gain. So the fully connected layer at the start basically is there to transform and do the composition of feature to gain. And the frequency distribution, spectral energy, temporal variation, pitch, phase, magnitude can be computed and fed into this feature, which then effectively computes the output gains. On the diagram below, this is a how the layers are connected and composed, which approximately shows there are about 88,000 parameters in this network that are trainable. It's not very deep because our need is to perform it at the edge. And as you can see, the input layer is connected to the VAD output GRU, which performs the VAD estimation, voice activity. And then the dense layer is concatenated with the remaining GRUs to get the output gains. So this is how the network is composed. The network setup and training. So the learning objective is basically a mean square error reduction of the predicted gain of the signal in discriminating noise and speech. So for training, what we used were the speech data from the public dataset, TSP speech from McGill, and the entity multilingual speech database for telephonometry, and additional data from the United Nations speech declaration, which is available. That's what is used for testing. So the noise data set from various sources were used, fan, AC, babble, street noise, dog, car, aeroplane, etc. And these were mixed at different levels to produce a wide range of signal to noise ratios. So a total of 6 hours of speech and 4 hours of noisy data is used to produce about 140 hours of noisy speech for training purposes. And spectral estimation of noise is then subtracted spectrally from the input for validation, and then adjusting the weight through the training process. So as we can see, the output loss tracks. We don't see a lot of overfitting here because the training loss and the validation loss are tracking quite closely. So from this, we think the results should be reasonable. So now about the implementation, the RNN model was trained in Python using Keras, and after training, the model was translated into C using Cython. C code was then converted into WASM, which is a WebAssembly. And the WebAssembly with JavaScript binding is used in Audio Worklet, which creates the processing node that we can consume in WebRTC. So Audio Worklet is a new technology, which is a modified or a 2.0 for web audio, which is a single-threaded processing. Audio Worklet is basically background processing in real-time audio applications. So effectively, what we have is a model that can be consumed in JavaScript using the WebAssembly, so that we can get appropriate performance. So the results on the top, we see the original signal for a sample noise and speech mix together, and this is a spectrogram which basically has the frequency distribution and the energy of all of the different mixed noise and speech. And as we can see, the clean signal after processing through this system, the black region is indicating silence, which means majority of the noise is suppressed, and the bands that are identified, which identifies the speech, is kind of extracted out. So the denoise signal is the one in the bottom. There were various research that we leveraged in getting to this, and the results are quite promising. So let's look at this system when integrated with BBM Enterprise Conference to see how well this works. We'll start with a loud AC or a fan type noise, which is a stationary noise, and then we'll progressively add different kinds of non-stationary noise, such as baby crying, dog barking, or a noisy street, a noisy office, etc., noisy restaurant, and then we'll see how well this performs. Okay, so let's toggle the noise suppression. So I would expect the sound to be suppressed. The next test will be a similar thing, except this time we're going to try out in a home setting where you're in a conference and there might be babies around, or maybe there's a baby crying, and you're trying to talk or in a conference not to distract the others. Let's see how that works in that environment. So we'll play the sound. Okay, let's turn on the noise suppression. So as you can see, the noise should be completely suppressed. Let's turn it back off. Okay, so this one we're going to try out another type of a sound. Let's say you're in a home and you have a dog, and there's a stranger that has come in and the dog's barking. So let's see how well that noise gets suppressed. So let's turn on suppression. So I would expect the noise suppression to be taking care of the dog barking. Okay, so the next demo is noise suppression, and the environment in this would be a busy mall where you have music playing and or radio jingles or type of noise, and you're trying to speak. And let's see how well it suppresses from that environment. So this is the sound. So let's turn on the noise suppression. So the noise I expect to be suppressed. Okay, so in this scenario, we're going to try out a noisy environment, such as a call center or busy office where there's telephone ringing, people talking, there is babble, and it's a large space, which is what makes the noise non-stationary as telephone calls and these noises mixed with people speaking. So we'll see how well the noise suppression in this environment works. So I'll play the sound here. So let's turn on the noise suppression. Okay, so I expect the noise to be completely suppressed. Okay, so this is a simulated environment where you're on a busy street. There is, again, it's a non-stationary noise coming in with vehicles moving around. There's honking going on. So you're in the middle of a street and you're trying to be in a conference. And so let's see how well that works. So the sound coming through now. Okay, so let's turn on the noise suppression. We're going to introduce a non-stationary noise with this plastic bag going from left to right. And this is a good test to see how this performs. So with denoise off, we're going to try out first. So you're hearing the noise, I'm sure. Nevin, can you hear?
Yep, I can hear it.
Okay, so let's turn on denoise, Mike.
Okay. And you can hear the noise has been eliminated. Shil, can you speak?
Okay, so I think that should be the test. Okay, so imagine we're in a noisy environment in a very large space. So Nevin, do you want to turn your simulation as well?
Okay, yeah, I'm at a loud restaurant right now.
Okay, so it's very difficult to hear. So, okay, so let's try denoise.
Yeah, and as you can see now, it's very quiet.
Okay, and you can hear my voice clearly, despite the background noise?
Yes.
I'm talking at a regular volume right now, or I can talk louder.